recording. Okay, so I turned on the recording now. Okay, so we're now recording. We just went over the homework, and I went over 10b using this theorem. And since AD minus BC is 0, the theorem implies that this given matrix is not invertible. Okay, and so I just said last class we proved the extended equivalence theorem, theorem 1.6.4. I stated this theorem, and now I'm giving this fundamental problem. Okay, so fundamental problem. Let capital A be a fixed m by n matrix. Find all m by 1 matrices, little b, such that the system of equations ax equals b is consistent. Okay, so that's the problem. The capital A is called the coefficient matrix, and so ax equals b is a system of linear equations. But okay, so basically the matrix little b is saying it's the values on the right side of your system. Okay, so let's look at a few cases. Okay, so let's look at 2 cases. Okay, so case 1. So for case 1, if you start with A is invertible, and what that implies is that AX equals B has the unique solution of X equals A inverse little b for every m by 1 matrix B. Okay, that's because if AX equals little b and A is invertible, you can multiply on the left side by A inverse and solve, and you get X equals A inverse little b. And that's for any little b you put here. And for any m by 1 matrix B you put here, you multiply both sides by A inverse on the left, and you have a solution, a unique solution for X equals A inverse B. This is if A is invertible, right? Only if A is invertible can you multiply the left side, you can multiply both sides of the equation on the left by A inverse. Okay, but case 2 is A is not square, or A is square, but not invertible. Okay, so in order to have an invertible matrix, it has to be square. So once it's not square, it can't be invertible, right? So, so either A is just not a square matrix, which means you can't use case 1, or it is square, but it's still not invertible. In either of those cases, case 1 doesn't apply, right? And it's every other possible case, right? If either A is invertible or A is not invertible. Now, if A is not invertible, it could be not invertible as a square matrix, or it's just not a square matrix and not invertible. Okay, so these 2 cases exhaust all possibilities of any matrix capital A. So in case 2, A is not square, or A is square but not invertible, and that implies that B must usually satisfy certain conditions. B must usually satisfy certain conditions in order for AX to equal B to be consistent. Okay, so we're not really here. I'm telling you the answer for case 1, and in case 2, this doesn't tell you the answer generally, but it gives you an idea of what an answer would be like. And so, let's look at example 3 and see how this plays out. So example C is determining consistency by elimination. Okay, so the question is, what conditions must B1, B2, B3 all three of them satisfy, in order for the system of equations, this system of equations, x1 plus x2 plus x3 is equal to b1. Also, next equation, x1 plus x3 is equal to b2. And the equation 2x1 plus x2 plus 3x3 is equal to b3. Okay, so what conditions must b1, b2, and b3 satisfy in order for this system of equations to be consistent? Okay, that's the question. B1, B2, and B3 are the components of a general 3x1 in this n by 1 matrix where m is 3 for the system AX equals B. Let me just put a note here. Note, if we represented this system as a matrix equation, as the matrix equation AX equals B, the little b here would be the 3x1 matrix, where the entries are B1, B2, B3. Okay, so that's where the b's are coming from. Right, I'll just point out, A would be the 3x3 coefficient matrix, which you just look at the entries here. So B1, 1, 1, 1, 1, 0, 1, and 2, 1, 3. That would be A. Okay, and X, little x, would be the 3x1 matrix, which would be x1, x2, x3. Screen's gonna bounce around again. Okay, so then, okay, so that's okay. So that's B, that's A, and that's X. Okay, so if you do this matrix times this one, you'll get x1 plus x2 plus x3, x1 plus x3, 2x1 plus x2 plus 3x3, and that'll equal this. Okay, so you can think about it and then do the multiplication and see how, remind yourself how that works. Okay, so anyway, so solutions to the problem, right? The problem is to find values of these three B values to make this linear system consistent. What are conditions on them to make it consistent? Okay, so the augmented matrix for the linear system is A equals this, right? This is the augmented matrix for that linear system. Oh, wait. That's the coefficient matrix, but then I'm going to add the B values. So this is B1, B2, and B3. Okay. So I'm partitioning the matrix here. I would draw a full vertical line here. So when it's just a small one, because I'm doing it on Word, I would normally have the vertical line completely from top to bottom there. Okay. And but anyway, we're partitioning the matrix. If you drew it small like that, that's also fine. But it's better if you do a full line. That way you're just making a clear demarcation of the left side and the right side. It's easier to read. Okay, so then the augmented matrix for the linear system is that one. It's not A. A is the coefficient matrix. So that's the augmented matrix for linear system. In reduced row echelon form, getting this matrix to reduced row echelon form, we get matrix. So this is that augmented matrix in reduced row echelon form. So I'm just going to plug in new values, what it is after it goes into reduced row echelon form. Give me a second. 0, 1, 1, 0, 0, 0. Then this is B2 minus B1 minus B1. This is B3 minus B2 minus B1. Okay, so what I did here was I just took this matrix and I applied Gauss-Jordan elimination, that whole procedure with all those 6 steps, right? You apply to that matrix, and at the end of it, it's in reduced echelon form. And so at the end of Gauss-Jordan elimination, you have that matrix in reduced echelon form, which is now this matrix. And so now you have this matrix, and the vertical line here is still the partition between the left side and the right side. Okay, getting this matrix to reduced echelon form via Gauss-Jordan elimination, we get the matrix, that matrix. Okay, from the third row, we can say,
bottom row.
Question?
Shouldn't there be a 1 in the bottom row?
No. So this when you have a matrix in reduced echelon form, you can have 0 rows. It's just the zeros have to be grouped at the bottom.
No, but it was 3, and then you minus 2. Shouldn't it be 1?
Wait. So there's lots of steps, right? When you get it to reduced echelon form. So it's okay. So if you start with
I just thought you were writing the steps when you said B3 minus B2 minus B1.
No. So I'm cutting to the chase. I'm saying the result of Gauss-Jordan elimination is that.
Okay, I believe you. All right.
Okay. So if you have this here, right, that's your original matrix. So then you have to apply all the steps. So
I just thought it was 3 1s the first line. I didn't realize it was a 2. I must have read it wrong. Sorry.
Oh, okay. You don't need me to go over that. Okay, so 2 1 3. Okay, we're good. Okay, so so that's the matrix in reduced echelon form, and from the third row, what the third row is telling you is that B3 minus B2 minus B1 has to equal 0. Right, and so because the left side equals the right side, and so the left side is 0 and the right side is that, and so you get that has to equal 0. And so there's your condition on the matrix. So so the system is consistent if and only if the third, so if and only if B1 if and only if B1, B2, B3 satisfy the condition that this equation holds. Or that B3 is equal to B1 plus B2. Okay, said another way, AX equals B is consistent if only if little b is a matrix of the form. So little b has components B1, B2, B3. So your B matrix here, where the first one's B1 and the second one's B2. Now that one's B3. So then you could write B1 plus B2 because that's B3. B3 has to equal B1 plus B2. Okay, so AX equals B is consistent if only if little b is a matrix of this form. So if little b is not a matrix of this form, where you have the first entry, the second entry, and then the third entry is the sum of the first two. If it's not of that form, then ax equals b is not consistent. If little b is of this form, then ax equals b is consistent. And you can go the opposite direction too. Okay, so that's the condition for example 3. Because we have this third row here, you need the left side to equal to the right side. And so that expression b3 minus b2 minus b1 has to equal 0. In order for this system to have solutions, okay? The solutions of this linear system are the same as the solutions of this one, because we only used elementary row operations via Gaussian elimination. Gaussian elimination only involves elementary row operations. And when you do an elementary row operation correctly to a matrix, it doesn't change the solution set of the corresponding linear system that it represents. And so when you get this matrix to reduce echelon form here, using only elementary row operations, all the solutions of this are the same as all the solutions of that. If this expression does not equal 0, then that would mean that the third equation is false. And so the only way all three equations can be true is if this equals 0. And then, since this can have solutions, so can the original one. And so when this equation holds, that means this system can have solutions, which means this system, which has the same solutions, can also have solutions. Okay? If that doesn't equal 0, then the third equation has to be false. And so that means this has no solutions, which means that that one also has no solution. Okay, so it's all determined by this one equation here. Okay, so example 4. What conditions must B1, B2, B3 satisfy in order for the system of equations x1 plus 2x2 plus 3x3 is equal to b1, 2x1 plus 5x2 plus 3x3 is equal to b2, and x1 plus 8x3 is equal to b3. And so what conditions must B1, B2, and B3 satisfy in order for the system of equations, to be consistent? Okay, so the augmented matrix is for that linear system. So on the left side, you have the coefficient matrix. Okay. Let's copy that maybe. Okay, so then the augmented matrix is 2, 1, 2, 3, 2, 5, 3, 1, 0, 8. Right, that's the left side because those are the coefficients. Right, and then this is B1, B2, B3, the right side. So this is your augmented matrix. Again, that vertical line could be all the way up. Okay, so that's the augmented matrix. So reducing this to reduced row echelon form, which remember the REF is the abbreviation of it. I just wrote it on words. We get, so what we get is now this matrix. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1 on that side. Now on this side, we get negative 40 B1 plus 16 B2 plus 9 B3. We get 13 B1 minus 5 B2 minus 3 B3. And here we have 5 B1 minus 2 B2 minus B3. Okay, so we now have that's weird. Okay, so we get that. So now that's in reduced Echelon form. So here we have no restrictions. So here we have no restrictions. On B1, B2, B3 in order for the linear system to be consistent. That's because when we take our original augmented matrix representing this linear system, we get to reduced Echelon form, we see that we have the solution where x1 is equal to this expression, x2 is equal to this expression, and x3 is equal to that one. So here we have no restrictions on B1, B2, B3 in order for the linear system to be consistent. We have the unique solution. X1 is equal to this expression. X2 is equal to this expression. And x3 is equal to this expression. Okay, so we have this unique solution. It's coming from this matrix here. For all values B1, B2, B3, and B3. So maybe you're asking, why did I use the word unique if I'm saying it applies for all B1, B2, and B3? Because I'm saying for each possible choice of values B1, B2, and B3. Let me word it that way. So no matter what values you choose for B1, B2, B3, if you fix that choice, so if you fix your choices of B1, B2, and B3, then when you get this matrix to reduced Echelon form, you get the unique solution of x1, x2, and x3, all in terms of the B1, B2, and B3 that you fixed. That makes sense? So if I chose B1 to be 0, B2 to be 0, and B3 to be 0, then I would get the solution x1 equals 0, x2 equals 0, x3 equals 0. See? If I change them all to 1, if I said, okay, I want B1 to be 1, B2 to be 1, and B3 to be 1, then x1 would be negative 40 plus 16 plus 9. X2 would be 13 minus 5 minus 3, and x3 would be 5 minus 2 minus 1. But those values for x1, x2, x3 would solve all three of these systems. It would work. You'd have to keep those values the way you chose them. So that would have to be 1. That would have to be 1, and that would have to be 1. But plugging in those corresponding values of x1, x2, and x3 would then solve all three equations in your system. Okay, so you always have this unique solution for any possible choice of values of B1, B2, and B3. So this is the other flip of the coin. In this case, you have a unique solution for any possible choice of values B1, B2, and B3. In the previous example, you needed a condition to be satisfied in order for the system to be consistent. And that condition was that B3 equals B1 plus B2. Okay, so in this problem, you have a condition on the B's in order for your system to be consistent. And in the next problem, there is no condition. And no matter what B's you choose, you have a unique solution in terms of those B values.
Professor, could I ask you to explain just, I'm not completely getting it. When you say B1 minus B2 equals B3, what does that mean? That if you subtract,
No, but B1 plus B2 equals B3?
yeah, does that mean like if you were, what are you adding together to get B3?
So, okay, it's a good question. So you have this linear system, right?
Yeah.
Okay. So, what was it? It was example 3. Okay, so what I'm going to do here is I'm going to have to write. I don't want to write here because I don't want to screw up the. So I'm going to put here. I'm going to put side notes. Notes about example 3. Okay, so we're talking about example 3 here. Okay, so we have this augmented matrix, right? So we have this matrix here, right? What I'm saying is that, let's say we took the value 1, 1, and 2, right? Right? For this matrix above, is it true that B1 plus B2 equals B3? Is that true or false?
So why for this one could you use different values for B, and for number 4 use the same values?
Well, so okay, so so follow me along my questions, and then I might answer your question, right? So for this matrix above, is it true that B1 plus B2 equals B3?
B1 plus B2. I mean, it
Let
like
me
just
ask you a
adding them
pre-question. What are
together.
the values of B1, B2, and B3
Are they just all the entries in the row?
on the column? So tell me what they are. What are they?
So it's on the column, not the row.
Correct. So it's the last column. It's this column here.
So B1 would be 1.
B2 equals
B2 equals 1
good, and B3
equals 2.
very good. Okay, so for this matrix above, is it true that B1 plus B2 equals B3?
Yeah.
So what my conclusion is saying, what the conclusion is saying is that since the matrix above satisfies the condition B1 plus B2 equals B3, then we know that the corresponding linear system to that augmented matrix is consistent, meaning it has at least one solution. Does that make sense?
Why does that mean it has one solution?
Okay, so good question. But so before that question though, does it make sense, the statement that I'm saying that because that matrix satisfies B1 plus B2 equals B3, that the corresponding linear system has solutions? Does that statement make sense?
I'm not sure why that means it's consistent.
Right. No, but those are two different questions, right? The question is, why does that mean it's consistent? But what I want to know is whether or not you understand this, whether it's true or not. It's not the question. What I mean is, do you understand the statement that says, if the condition B1 plus B2 equals B3 is satisfied, then this
I get that.
That makes sense?
Yeah.
Okay, good. So if I gave you another matrix where B1 plus B2 is not equal to B3, then that statement is saying that the corresponding linear system has no solution. Does that make sense?
Okay.
Okay. So now another question, right, is why is that true, right? So what the argument is saying is that you have your original linear system, right? And you have the augmented matrix representing that linear system. Does that make sense so far?
Yeah.
Okay. Now you get this matrix to reduce echelon form using Gauss-Jordan elimination. That means you get it to reduce echelon form using only elementary row operations. That means that as you get more matrices from after each elementary row operation, those matrices correspond with linear systems, and those linear systems have the same solutions as the original one, because elementary row operations do not change solutions. Does that make sense?
Yeah, I get that.
Okay. So now this matrix also represents a linear system, but because we attained it by a sequence of elementary row operations, it has the same solutions as the original one. Does that make sense?
So what happened?
Wait. Does that make sense?
It makes sense.
Okay, let me keep going. But that makes sense so far?
Yeah, I get that.
Okay, so next, so the solutions of this linear system is the same as the solutions of the original one by what I just said. So now you say, okay, what are the solutions of this linear system? Well, what if B3 minus B2 minus B1 does not equal 0? Then the third equation is saying 0x1 plus 0x2 plus 0x3, which is 0, right? It's saying that 0 is equal to B3 minus B2 minus B1. But if B3 minus B2 minus B1 is not 0, then the third equation is saying 0 equals something that's not 0. And so if B3 minus B2 minus B1 does not equal 0, then the third equation is false, which means that this linear system has no solutions, no matter what x1, x2, and x3 you plug in. Does that make sense?
Just one thing I'm confused about, the second side of the augmented matrix now. So you got the right side to reduce row echelon form, but the left.
No. So wait, you're saying augmented, this whole thing is the augmented.
Yeah, so in its current state, did you do the same thing you did to the right side, to the left side, to get these expanded values, B1 and then B2 minus B1 and then B3 minus B2 minus B1? Where did you extend how did you change the B's from the previous form?
So the steps to do get this to reduce echelon form, right? You would add, like the first step would be adding -1 times the first row to the second, so that this entry would be a 0.
Yeah.
And then that would result in this entry being B2 minus B1.
Oh, okay. So that's
See that? And then you would just keep doing that, and then at the end you would have all this.
Okay, yeah, that's just what I was confused about, because yeah,
A good exercise would be if you did this yourself, getting this to reduce echelon form and seeing how you get that.
yeah, okay, I'll try and do that after.
Okay, so you get this to reduce echelon form. So for this class, even though I would like to show all the steps, doing the whole procedure every time we have it takes so much time, I can't do it every time. So, but all I have to do is just say you get it to reduce echelon form by Gauss-Jordan elimination, because we went over Gauss-Jordan elimination. It's a set procedure. So the thing I'm saying to do in this step is a set thing. And so once you understand Gauss-Jordan elimination, this step is explained by that statement, if that makes sense. So, okay, so you get this to this, and then because the solutions stay the same, the only way that this matrix can have solutions is if this equation holds. And if it does, then this has solutions, which means this does. If it doesn't hold, this doesn't have solutions, which means that doesn't. Make sense?
Yeah, thank you.
Okay, you're welcome. Good. Okay, so that's the end of 1.6. Okay, so I'm going a little fast because we have a lot of material to cover. So the next one is 1.7, which is on diagonal, triangular, and symmetric matrices. Okay, so the first thing is on diagonal matrices. So definition is a square matrix in which all entries off the main diagonal are 0 is called a diagonal matrix. Okay, so here are some examples. Okay, so it's just all the entries off the main diagonal are 0. That's a diagonal matrix. So for instance, in this one, if you had 1, 0, 0, -3, that's a diagonal matrix because all the entries off the main diagonal are 0. The main diagonal goes from the top left to the bottom right, just like y equals -x. It just goes across the diagonal like that, right? So that is a diagonal matrix. Another example of a diagonal matrix would be the 3x3 matrix, would be the 3x3 identity matrix. So this is also a diagonal matrix. because all the entries off the main diagonal are 0. Okay. Another example of a diagonal matrix would be the matrix where you have 0, 0, 0, 0. The enemy 0 matrix is also a diagonal matrix, because the only thing that you need for to be a diagonal matrix is be square, and all the entries off the main diagonal are 0. So for instance, you need this entry to be 0, and you need this entry to be 0 in order for it to be a diagonal matrix. There's no restriction on the entries on the main diagonal. And so if all the entries on the main diagonal are also 0, making a 0 matrix, it's still a diagonal matrix. So all three of those are examples of diagonal matrices. So a general n by n because it has to be square by the definition, a general n by n diagonal matrix can be written as, so usually use the notation D for diagonal to represent a diagonal matrix. And let me see here, maybe I can do this. Okay, so let's say you have D1, D2. These are the entries on the main diagonal. And then this is like D3, and then dot, dot, dot. And this is the last one, Dn, because it's n by n. Then everywhere else it's 0. So 0, 0, 0, 0, 0, 0, 0, 0, dot, dot, dot. 0, 0, 0, 0. Everywhere else is 0. I'm putting dot, dot, dots, and there's zeros here too, but the matrix continues. Okay, so, oh, wait, this should be dot, dot, dot. So, okay, so this is a general n by n diagonal matrix where D1 is the entry in the first row or first column on the main diagonal. D2 is the entry on the second row or second column of the main diagonal, and so forth. Since it's an n by n, the Dn entry is in the nth row and nth or nth column. Okay. So I'm going to denote this by a 1. So if I want to refer to this, I'll refer to it as 1. A diagonal fact. A diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. Okay, so remember, if and only if means that the two statements have the same truth value. So one statement is this one, and the other statement is all of its entries on the all of its diagonal entries are non-zero, right? Okay, so a diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. So this matrix, for instance, this 0 matrix, right? Right. So if you looked at the 0 matrix, so this matrix has does not have all of its diagonal entries as non-zero numbers. Does not have all of its diagonal entries. Does not have all non-zero diagonal entries, right? In fact, they're all 0. So since it doesn't have all non-zero entries, then that implies by the above fact that that matrix is not invertible, right? By the above fact, right? So since this is false, that's also false because they're the same in truth value. So knowing that this is false for this matrix means you know that this is false for that matrix. This is easy to know. You just look at the entries. Are they all 0 or are they not all 0? I mean, are all of its entries non-zero, or is it false that all of their entries are non-zero? Okay. Okay, good. Okay. So in such a case that the matrix capital D is invertible because all of its diagonal entries are non-zero, the inverse of 1 is the following. So now we want the inverse of this matrix in 1. So the inverse of a matrix D is denoted by D inverse like that. And so D inverse then is going to be this matrix. Okay, so now the entries on the main diagonal would just be their multiplicative reciprocals, 1 over D1, 1 over D2, 1 over D3, dot, 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 1 divided by Dn. Okay, so now we're just taking the reciprocal of each of those D values in the main diagonal, and off of it will all be zeros. All the entries in the dot, dot, dot are 0 entries. This is a general matrix for an n by n. And so that's why I'm using the dot, dot, dots, because we can use any number of rows or columns in this argument. And the dot, dot, dot will fill in the rows and columns that are left out. Okay? And so that's the form of an inverse of a diagonal matrix, as long as all the entries on the main diagonal are non-zero. Okay. If the matrix capital D is the diagonal matrix represented by 1, meaning this one. So if capital D is a diagonal matrix represented by 1, and K is a positive integer, right? So that means, right? So that means that K is an element of the set 1, 2, 3, 4, 5, dot, dot, dot. This means is in the set. So K is in the set, in that set. So, and K is a positive integer, meaning K is in this set. So K is 1 or K is 2 or K is 3 and so forth, positive integers. So if D is a diagonal matrix and K is a positive integer, then D to the K, meaning the kth power of D, is equal to the following matrix. So you just take all of these entries and the entries on the main diagonal, you just raise it to the kth power. So it's D1 raised to the kth power, D2 raised to the kth power, D3 raised to the kth power, dot, 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 D sub n raised to the kth power. Okay, good. So then, okay, so that's D to the K. Right, so now you can find the inverse or power of a diagonal matrix as long as it's invertible. Right? K is a positive integer. Okay, so example 1, if you have a given matrix A and it's equal to this 3 by 3 matrix, 1, 0, 0, 0, negative 3, 0, 0, 0, 2, then A inverse, the inverse of that, right? We're just applying this thing here because we have a diagonal matrix where all of its entries are non-zero, right? So then since capital A is a diagonal matrix such that all of its entries on its main diagonal are non-zero. And A inverse is just equal to the 3 by 3 matrix where we just do 1 over the multiplicative reciprocal of each entry. That's A inverse. Right? And we could do that because all of its entries on its main diagonal are non-zero. So it's invertible and it do it that like that. Okay, you could write if this is 1, not 1 over 1. You could just write 1. I'm just doing 1 over 1s to illustrate the fact that you're doing 1 over these numbers for each one. You could write negative 1/3 instead of 1 over negative 3. Okay. Also, if you take this matrix A and you raise to the 5th power, then what you get is, well, all the entries off the main diagonal is still 0. And by this formula here, you're just taking all the entries on the main diagonal in the original D and you're raising it to the kth power, where k is a positive integer. Okay. And so that means that this, since the original A had 1, -3, and 2 as its diagonal entries, you just raise each of them to the 5th power because it's A to the 5th. The 5 here is we're getting 5. And so that's -3 raised to the 5th power. And then this one is the number 2 raised to the 5th power. So I'm just raising each of the main diagonal entries corresponding to the 5th power. Okay, and then you do the operation of what they are. And 1 to the 5th power is 1. -3 to the 5th power is -243. 3, 9, 3. And 2 to the 5th power is 32. Okay, and then everything else is 0. Okay, so that's A to the 5th power. And then if you do A to the -5th power, well, A to -5th power, you can think of it as A inverse to the 5th power. Okay, so since we had A, all of its main diagonal entries are non-zero, so it's invertible. So we found A inverse. So we have A inverse, and so A to the -5th power is A inverse to the 5th. And so you're just taking this matrix and you're raising it to the 5th power. And so since it's this matrix, so you're taking this matrix and you're raising it to the 5th power. And so when you take that matrix and raise it to the 5th power, you're just taking all the main diagonal entries and raising them to the 5th power, just like you would for the original matrix A when you did to the 5th power. So this is 1 to the 5th power. This is -1/3 to the 5th power. And this is 1/2 to the 5th power. And then everywhere else is 0. Okay, and so then you just do that calculation. 1 to the 5th power is 1. -1/3 to the 5th power is -1 over 243. This 3 to the 5th power is 243. And it's just -1 over that. And then 1/2 to the 5th power is 1 over 32. And that's because 2 to the 5th power is 32. So 1/2 to the 5th power is 1 over 32. Okay, and everywhere else is 0. Okay, so A to -5th power is this matrix right here. Any questions about any of this? Okay, let's go. Okay, so matrix products that involve diagonal factors are easy to compute. Okay, so examples. Okay, So now these are examples of multiplying matrices where at least one of them is a diagonal entry, as a diagonal matrix. So for instance, let's say you have this 3 by 3 matrix where the diagonal entries are D1, D2, and D3. All the other entries are 0. Okay, and so let's say that's you left multiplied an original matrix, 3 by 4 matrix. So that this diagonal matrix, you multiply on the left with that from the original one, which was A11, A12, A13, A14. This is just a representation of a general 3 by 4 matrix. Okay, and so this is A sub 3(1), this is A sub 3(2), this is A sub 3(3), this is A sub 3(4). So okay, so this is a general 3 by 4 matrix, and you left multiply it by a diagonal matrix. So what happens is what you get. This is a, if you think about what the sizes are, I'm going to bring this down. Okay, so this is one line. Okay, so you have a 3 by 3. That's a 3 by 3, and the other one is a 3 by 4. Right? So you're multiplying a 3 by 3 matrix by a 3 by 4 matrix. So the inner entries are the same, right? So this entry is the same as this entry. Those two entries are the same. And so it's the outer entries that are going to tell you the size of the resulting matrix. So your resulting matrix is a 3 by 4 matrix. Yeah, so your resulting matrix is a 3 by 4 matrix determined by the outer entries because the inner entries are the same. And so when you multiply this out, if you do all the multiplication, what you see is that you get D1, A11, D1, A12, D1, A13, D1, A14. You just multiplied the first row by D1, and then you multiply the second row by D2. So you get D2, A21, you get D2, A22, you get D2, A23, and you get D2, A24. Okay, so you multiply the second row by D2. Then you multiply the third row by D3. So you get D3, A31, D3, A32, D3, A33, and D3, A34. Okay, so you just multiplied each row by the corresponding B. First row by D1, second row by D2, third row by D3. So left multiplying by a diagonal matrix just results in multiplying the rows of this matrix by the corresponding entries on the main diagonal. See that? Okay, and so that's what that does. And then if you take, okay, so examples. So this is the first example. Okay, so let me call it example 1. Okay, so example 1. That's example 1. Okay, so example 2. If you have so if you have a matrix on the left side, and you right multiply it by a diagonal matrix, for instance, in this case, so you right multiply it by a diagonal matrix, then you get a resulting matrix. Now, the matrix on the left is 4 by 3. And the matrix to the right of it is already a 3 by 3 matrix. So you're multiplying a 4x3 matrix by a 3x3 matrix. So the entries, the inside entries are the same. The two inside entries are the same, which means you can multiply them. And then that means the outside entries determine the size of the resulting matrix. So your resulting matrix is now a 4x3 one. The first one was 3x4. This one's 4x3. And so that means that you now have a 4x3 resulting matrix from the product of those two matrices. And so, good. So now you have a 4x3 matrix determined by the outer entries. So this is a general 4x3 matrix. So this is A11, A12, A13. This is A21. This is A22 and A23. A31, A32, A33. This is A41. This is A42. And this is A43. Okay, so this is a general 4x3 matrix, and right multiply it by a diagonal matrix. And so now try multiplying. So if you multiply the first row here by the first column here, what you see is that this entry is going to be D1, A11. But now multiply the second row by the first column. So then that's this entry, and you get D1, A21. And multiply the third row by the first column, and you get D1, A31. I just switched, instead of saying A31, D1, I wrote D1, A31. And then this would be D1, A41. And so what happens is the resulting matrix, you're multiplying the original one, the first column, by D1. And then the same thing happens for D2. You have D2 for the second column, you have D2, A12. You have D2, A22. You have D2, A32, and then D2, A42. So that's the second column. And then the third column is just multiplying by D3. So D3, A13, D3, A23, D3, A33, and then D3, A43. Okay. So right multiplying by a diagonal matrix means you're multiplying the columns by the corresponding diagonal entry. So multiplying the right by diagonal matrix means you multiply the first column by D1, the second column by D2, and the third column by D3. Okay. And if you change the size of the matrices, the pattern continues. So if this was a 5x4 matrix and this was a 4x4 diagonal matrix, you would just multiply the first column by D1, the second column by D2, the third column by D3, and the fourth column by D4. Okay, so the pattern will continue. So right multiplying by a diagonal matrix means multiplying the columns. Left multiplying by a diagonal matrix means multiplying the rows. That's what these two examples illustrate. Okay, so example 1 illustrates that left multiplying by a diagonal matrix results in multiplying the rows of the original matrix by the corresponding diagonal entries of the diagonal matrix. So example 1 illustrates that left multiplying by a diagonal matrix results in multiplying the rows of the original matrix by the corresponding diagonal entries of the diagonal matrix. That means that the first entry in the main diagonal is D1, so you multiply the first row by D1. The diagonal entry in the second row is D2, so you multiply the second row by D2 and so forth. Okay, and example 2 illustrates that right multiplying by a diagonal matrix results in multiplying the columns of the original matrix by the corresponding diagonal entries of the diagonal matrix. Okay. Okay, so that's what this is explaining. Okay, definition. A square matrix in which all entries above the main diagonal are 0 is called a lower triangular matrix. A square matrix in which all entries below the main diagonal are 0 is called an upper triangular matrix. Okay. A matrix that is either upper triangular or lower triangular is called triangular. So this defines a lower triangular matrix. It defines, the first sentence defines a lower triangular matrix. The second sentence defines an upper triangular matrix. And the third sentence defines a triangular matrix. Okay, so definition. A square matrix in which all entries above the main diagonal are 0 is called a lower triangular matrix. It sounds like the opposite, but if all the entries above the main diagonal are 0, then the only non-zero entries are below or on the main diagonal. That's why it's called a lower triangular matrix, because that's where you look the lower part to find the non-zero entries. Okay, a square matrix in which all the entries below the main diagonal are 0 is called an upper triangular matrix. Same idea. To find non-zero entries, you either need to be on the main diagonal or above it. So that's why it's called an upper triangular matrix. A matrix says either upper triangular or lower triangular is called triangular. Okay, so examples. So, for instance, if you have a general, okay, let's do it. Okay, we'll do a general 4x4 diagonal matrix. Sometimes it's fun making these matrices. Okay, so let's say we have this. We have A11, we have A12, A13, A14. That's 0. That's A22. That's A23, A24, and then this is 0, 0, A33, then A34. This is 0, 0, 0, and then A44. Okay, so this is an example of an upper triangular matrix. This is a general 3x4 upper triangular matrix. Okay, it's a general one because I'm using, instead of putting numbers in these entries, I'm putting variables, right? I'm putting these variables here because these could be any values, but the other ones have to be 0 because it's an upper triangular matrix, right? An upper triangular matrix is a square matrix in which all entries below the main diagonal are 0. All entries below the main diagonal are 0 to be upper triangular, right? So all the entries below the main diagonal are 0, and so this is a general 4x4 upper triangular matrix. It's 4x4, 4 rows and 4 columns. Okay, so now if you have this matrix, so I'm going to do another 4x4 matrix. So now we're going to have A11, A21, A31, and A41. And then this is A22, this is A33, this is A44. These are entries below the main diagonal now. Also, so this is A32, this is A42, and this is A43. Okay, and so now here we're going to have all the entries above the main diagonal are 0. And so it doesn't line up perfectly. Oh, wait, I can make it though. There we go. Okay, so then that matrix is a general 4x4 lower triangular matrix. Okay, that's because it's a lower triangular matrix because all entries above the main diagonal are 0. All entries above the main diagonal are 0. And we have variables in every spot that doesn't have to be 0. They could be 0, they don't have, but they don't have to be. So we have a variable for all the other spots. But all these other 6 places have to be 0 for this 4x4 matrix to be lower triangular by the definition. Okay, and this can apply to any size square matrix. So you could have a 5x5 square matrix be upper or lower triangle. You have a 1x1, 2x2, 3x3, 10x10, any size square matrix you want. There are diagonal, there are upper and lower triangular matrices. Okay, so note both of the general matrices above are also triangular, right? Because a triangular matrix is one that is upper triangular or lower. So all of these matrices are upper triangular, so they're triangular. And all of these matrices are lower triangular, and so they're also triangular. Okay. Remark. A diagonal matrix is both an upper triangular matrix and a lower triangular matrix. Also, a square matrix in row echelon form is upper triangular since it has zeros, since it has only zeros below the main diagonal. Okay. Remarks, I'll say. A diagonal matrix is both an upper triangular matrix and a lower triangular matrix, right? So if you look at for instance, if you look at an example of a diagonal matrix D, some of the examples. For example, I add another one. Example, if you have a matrix, this is not the general D from before, now it's a specific diagonal matrix. If you look at a particular diagonal matrix here, where this is, let's say 1, 2, 0. So this is a diagonal matrix. Then it's upper triangular because all entries below the main diagonal is 0. It's also lower triangular because all entries above the main diagonal is 0. Okay, so this matrix D is a diagonal matrix. Also, by checking definitions, you can see that capital D is also an upper triangular matrix and a lower triangular matrix. Also clearly, D must be a triangular matrix. Okay, So any diagonal matrix will be both upper triangular and lower triangular. So this is an example of a particular diagonal matrix where we see it has to be upper triangular and lower triangular, and also has to be a triangular matrix. Okay, that's explain this first remark here in the first sentence. Also, a square matrix in row echelon form is upper triangular, since it only has zeros below the main diagonal. So for instance, if you look at matrix capital A, let's say you look at the matrix A, and it's this, let's go with, oops, oh, that would be good, but not now. Okay, so this looks like an easy one. So what do I want to say? It's so, all right, let's do it. 1, 2, 3, 4. Okay, so if you look at the matrix A here, after getting it to row echelon form, we get the matrix. So we get this matrix to row echelon form, and so when you get this to row echelon form, you add -3 times the first row to the second row. And so you have a 0 here, and you have a -2 here, because it's -3 times 2 is -6, -6 is -2. Now you have this. Well, oh wait, so then we need to multiply the second row by -1/2. We'll get that. Okay, so this matrix has every non-zero row has a leading 1. All the 0 rows are at the bottom. Property 1, every non-zero row has a leading 1. Check. Second property, all the zeros at the bottom. Check. It's true vacuously because there are no 0 rows. And property 3, if you have 2 consecutive non-zero rows, the leading one, the lower one, is further to the right, the leading one above it. That also is true. So this fits all 3 properties for a matrix to be in row echelon form. And there's more than one way sometimes to get a matrix in row echelon form. Okay, so actually, there's always more than one way, I think, except it's a 1-by-1 matrix. Other than that, once it's larger than a 1-by-1 matrix, there should be infinitely many ways. So this is one of the infinitely many ways to get this matrix A in row echelon form. But when you look at this matrix, you see that is upper triangular because all the entries below the main diagonal are 0. Okay, so what we see is that a particular is that when we got matrix capital A to some row echelon form, because we could do it in many ways, we got a matrix that was lower triangular. And this always happens. Whenever you take a given matrix and you get it to row echelon form, the result is a lower triangular matrix. Okay? It has to do with the definition of a matrix in row echelon form. Every non-zero row has to have a leading 1. All the 0 rows have to be on the bottom. And when you have 2 consecutive rows that are non-zero, the leading one and the lower one has to be further right than the leading one above it. And so that means there's always a shift to the right of each next one. Okay, so like if you thought, I'm going to go whiteboard for a second. So if you think about what that means for a matrix to be in row echelon form. If the first row has to have a leading 1, right, and the other entries can be anything you want them to be, right? The next row, the leading 1 has to be to the right of the last one. See, this could be a 0 row also, but let's say it was that. So you already have that there are only 0 entries below the main diagonal, right? Because this is the main diagonal here. Because now you have a shift to the right. Now you could have another non-zero row. But if you have another non-zero row, the leading 1 in the next row has to be further to the right than one before it. And so now you see that you still have only zeros below the main diagonal. Now you could have another non-zero row, which means that the leading one has to be shifted to the right again. there's only there's x's there, and that's fine. So you see, there's still now. If you had a all zero row, if everything else was all zeros, with dot dot dot, this continues. Now let's say you had an all zero row. Well, that would just mean that there would have to be zeros below the main diagonal, because if everything is zero, then all the entries below the main diagonal in that row would also be zero, right? All the zeros are at the bottom. So any matrix in row echelon form has to be upper triangular. All the entries below the main diagonal have to be zero. Okay? That's by the definition of a matrix in row echelon form. Okay, so next, so 4 facts about triangular matrices.
Can't you have one in row echelon form where there's like a 1 in the first column, a 1 in the second column, and then a 1 in the fourth column? And that wouldn't be a triangular?
Well, so you want a 1 in the first row or column?
1 in the first column, and then the second row in the second column.
Well, so wait. So a leading 1 is defined by the row it's in. A leading 1 is the first non-zero entry in the row it's in.
Yeah, so let's say there's a gap between 2. So you get in the second row, you have in the second column. And then let's say in the third row, you have in the fourth column.
Okay, so you want the first column and the second column and the fourth?
No, so and then in the third row, not the third one. Instead, you had the fourth one. It was
Yeah, but you're saying you want a 1 in the first, the second, and the fourth. That's what you said, right?
No, in the third row, in the fourth place.
Oh, okay. Now I see what you're saying.
So that's
okay. Okay.
That's in row echelon form, but it wouldn't be a diagonal, would it? So it wouldn't be triangular.
So don't forget, we're not saying the matrix has to be diagonal. We're just saying it's in row echelon form.
But would this be a triangular?
So, right. So the conclusion is that it's upper triangular, meaning all the entries below the main diagonal are zero. So let's just enumerate. Let's just be specific about where the main diagonal is, right? It's right there. So I'm going to make the size of this matrix so that that's the main diagonal. Okay, so good question. So let's say you have that, right? Let's say you have another leading 1, but the leading 1 has to be here, right? Because it has to be to the right.
Yeah.
So that means that all the entries now have to be 0. In fact, it's less. This fails to be. This will be. It's even more certain that this will be upper triangular, because before, in the case I put above, the non-zero entries are as close as possible to the lower half. Do you see that?
Yeah.
In your case, instead of saying there's always a 1, you're now saying, okay, there's going to be a row where I'm going to move. Well, the leading 1, I made my leading ones as far left as possible, right, to try and get it to be on the left, underneath the main diagonal. Now that you've moved it to the right, you've actually made it even more an upper triangle. Not more, but you see what I mean? There's no way it's going to be below the main diagonal non-zero entry, because now the 1s are now shifted further to the right, which means the zeros are going to extend further to the right, which means there's definitely going to be all 0 on the left. You see that?
So you just kind of start the diagonal from the top and then follow it as like all the way along the diagonal, even if there's zeros?
Well, see, you don't have to have all leading 1s in the diagonal, but the leading 1s always have to be further to the right, which means that if you want a non-zero entry on the left, you somehow need a leading 1 to be to the left of the main diagonal, but it can't be, because you always have to shift it to the right one. You see that?
Okay.
Right? If the leading 1 always has to be shifted to the right one every time you move down, then that means there always has to be zeros on the left.
Yeah.
Right? And even if there's not a leading 1 on the main diagonal and you move it to the right, then there's still all zeros to the left of it, which means there's only zeros on the left of the main diagonal.
Yeah.
Okay, you get it?
Yeah, so these are both upper triangular or
Right,
lower?
so these are both in row echelon form, and they're both upper triangular.
Upper triangle. Okay.
Right, this matrix is green. This is an upper triangular matrix. This is upper triangular. It's upper triangular because all the entries below the main diagonal are 0. You can kind of think of it as the opposite of the definition. The definition is saying all entries below the main diagonal, and that means it's upper triangular. All entries above the main diagonal are 0 means it's lower triangular. Okay. Okay, good. Okay, so the good question though, because your first thought might be, well, why don't I just move the ones, right? Couldn't that? But you see how it only makes it worse. It only makes it the best case scenario for failing. The worst case scenario is that all the ones are on the main diagonal, because that's as far left as you can make the entries as non-zero. Once you push them to the right, there's no way it's going to be there's no way it's not going to be upper triangle. Okay, so these are 4 facts about triangular matrices. Okay, so before I do these 4 facts, what I'm going to do is I'm going to have a picture. And so how do I want to do this picture? So actually, I'm going to do this on the whiteboard. Okay, this is going to be on the whiteboard. Okay, so I'm going to go to the whiteboard. The reason I'm doing it on the whiteboard is because the picture, I don't want to do this picture on Word. Okay, so so if you have a matrix, right, and you look, there's the main diagonal. But then if you look at the entries below the main diagonal, it means I is greater than j, and above the main diagonal is I is less than j. And what do I mean by that? So I'm using the notation for this square matrix, saying that the matrix we are considering is a square matrix, capital A, which is equal to A sub ij. So I'm going to write that in. Let me just. So this is the matrix A sub ij. So that means that the row that this entry is in is row I, and the column it's in is in column J. So when you look at these entries A sub ij, then when I is greater than j, it's below the main diagonal. And when I is less than j, it's above the main diagonal. So if you were to look at a 3x3 matrix, A11, A12, A13, A21, A22, A23, and A31, A32, and A33, then, right, this is the main diagonal. But now the entries in which I is greater than j are these entries. See how the entry, the I entry, the first one is greater than the second entry. 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. All the entries in which I is greater than j is below the main diagonal. Now all the entries in which I is less than j is above the main diagonal. So A12, I is less than j. 1 is less than 2, 1 is less than 3, 2 is less than 3. So all the entries A sub ij in which I is less than j is above the main diagonal. All entries A sub ij in which I is greater than j is below the main diagonal. You see the color quote. The blue entries here correspond with the blue here, and the green entries here correspond with the green here. The purple corresponds with the purple line here. So I'm going to draw this as a purple line. That way you can see how that's the main diagonal. Okay, so that's that. Okay, so the matrix we're considering is a square matrix A, A represented A little a sub ij. Right, lowercase a is for the entries, and upcap A is for the entire matrix, and the ij is for which entry. Okay, so now I'm going to talk about square matrices. So fact one is that a square matrix, capital A, denoted as A sub ij, right, by little a sub ij, I'm going to fill that in. Okay, so A sub ij is upper triangular if only if all entries to the left of the main diagonal are 0, right? So we know that already. But now that means something else. That is, if you have an entry A sub ij, fill that in. Wait, let me just type this. And then A sub ij is 0 if I is greater than j. Okay, so good. Okay, so now let me just fill this in for a second. If you have a matrix A sub ij, okay, that is little a sub ij equals 0 if I is greater than j. Okay, so a square matrix capital A equals A sub ij is upper triangular if only if all entries to the left of the main diagonal are 0. That is, little a sub ij is 0 if I is greater than j. Okay, saying that a matrix is upper triangular means that all the entries that I circled in blue are 0. All the entries to left or below the main diagonal. But those entries that I circled in blue are entries A sub ij in which I is greater than j, right? A sub 2, 3, A sub 3, 1, A sub 3, 2. Those are all entries in which the number I is greater than the number j. And so if you have the condition on a matrix that for every entry A sub ij such I is greater than j, A sub ij equals 0, that means your matrix is upper triangular. So this is another way to define an upper triangular matrix, or to show that a matrix is upper triangular. Instead of looking at the matrix and saying, okay, I see all the entries below the main diagonal are 0, so it's upper triangular. Instead, if you prove that if I is greater than j, that A sub ij is 0, then that would be proving your matrix was upper triangular, because it'd be showing that all the entries below the main diagonal are 0. That was a little fast, but does that make sense? Okay, so these are facts about triangular matrices. Okay, the second fact, fact 2, okay, so a square matrix, capital A, the same square matrix, capital A, little a sub ij, fill that in, is lower triangular if only if all entries to the right, or all entries to the right of the main diagonal are 0. That is, A sub ij is equal to 0 if I is less than j. So now I'm just going to fill in the ij part here. So this is matrix capital A equals little a sub ij. That's A sub ij. Is lower triangular if only if all entries to the right of the main diagonal are 0. That is, A sub ij is equal to 0 if I is less than j. So see the green, right? The green entries here are all the entries in which I is less than j. And so if all those entries are 0, that means it is lower triangular. Okay? It's just writing it a different way, the same definition. Okay, so you can approach the problem of finding whether or not a matrix is upper or lower triangular in different ways. This way is using these entries, right? So the third fact, number 3, the third fact is a square matrix, capital A equals, again, A sub ij is upper triangular if only if its only if the ith row starts with at least I minus 1 zeros for every I. Okay, so a square matrix A equals A sub ij is upper triangular if only if the ith row starts with at least I minus 1 zeros for every I. Okay, so let's look at another example. Let's look at a 3x3 matrix, except instead of using general symbols for the above, I'm just going to use numbers now. So let's say you had 1, 2, 3, 0. Stick with 1, so it's easy to see 0, 0, 1. So this matrix is upper triangular. But you can also see is that the first row starts with 0 with at least zero many zeros. The second row starts with at least 1 0. And the third row starts with at least 2 zeros. So this statement that the ith row starts with at least I minus 1 zeros for every I is saying that if you look at any particular row and you think of the row number, it has to start with the row number minus 1 many zeros. So the second row starts at least 1 0. 2 minus 1 is 1. The third row starts at least 2 zeros because 3 minus 1 is 2. That's what that statement is saying. But that statement is equivalent to the statement that your matrix is upper triangular. So a square matrix A is upper triangular if only if the ith row starts with at least I minus 1 zeros for every I. Equivalent means that they have the same truth value. Those two statements have the same truth value. So saying that a square matrix is upper triangular has the same truth value as the statement for every I, the ith row starts with at least I minus 1 zeros. Okay, and so you see in this particular example with numbers that statement holds, and it's also upper triangular. So both those statements are true. It's an example of how this if and only if statement is true for a particular matrix. Okay, and now the fourth fact about triangular matrices, fact 4, is that a square matrix, you can hear me, right? Okay, so good. Okay, a square matrix, capital A equals A sub ij is lower triangular if only if the the jth column starts with at least j minus 1 zeros for every j. So I'm just going to fill in the ij. So a sub ij. So the I is kind of okay, so a sub ij. So I guess okay. So square matrix A capital A equals A sub ij is lower triangle if only if the jth column starts at least j minus 1 zeros for every j. So let's look at another 3x3 matrix. And this one is going to be lower triangular, which means all the entries above the main diagonal are going to be 0. I'm choosing to keep all the entries on the main diagonal 0 because it's just the worst case scenario. If some of them were 0, just okay. So so square matrix capital A equals A sub ij is lower triangular. Wait. Yeah, it's lower triangle, all the entries above the main diagonal 0. Okay, so a matrix capital A is lower triangle if only if the jth column starts with at least j minus 1 zeros for every j. So the first column starts with 0 zeros. The second column here starts with 1 0, and the third column starts with 2 zeros. Columns are vertical, right? So you see in this matrix that the statement the jth column starts with at least j minus 1 0 for every j is true for this matrix I just drew, and it is also lower triangular because all the entries above the main diagonal are 0. So both statements are true for that matrix, and this statement is saying one statement infinitely at the other. So that's true. They're both the same truth value. They're both true, right? They could both be false, but in this case, they're both true, right? So this is another way of identifying which matrices are lower triangular. You could identify a matrix as being lower triangular if you find that the jth column starts with at least j minus 1 zeros for every j. Okay, so if you only know that the jth column starts with, if you know that the jth column starts with at least j minus 1 zeros for every j, without seeing that all the entries above the main diagonal are 0, you still know it's lower triangular. Okay, so that's the idea for fact 4. So those are 4 facts about triangular matrices. Okay, now I'm going to go back to to Word. Okay, next is theorem 1.7.1. So part A says the transpose of a lower triangular matrix is upper triangular. And the transpose of an upper triangular matrix is lower triangular. Okay? If you switch the rows and columns, if you take the transpose of the matrix, you switch the rows and columns. And if you do that, you start with the lower triangular and it becomes upper triangular. And if you switch rows and columns of an upper triangular matrix, it becomes a lower triangular. Okay. B, the product of lower triangular matrices is lower triangular. The product of upper triangular matrices is upper triangular. Okay, simple. If you multiply lower triangular matrices, you get a lower triangular matrix. If you multiply upper triangular matrices, you get an upper triangular matrix. C, a triangular matrix is invertible if only if its diagonal entries are all non-zero. Okay, so a triangular matrix is invertible if only if its diagonal entries are all non-zero. This is different than when we talked about a diagonal matrix, right? For a diagonal matrix, we found a diagonal matrix is invertible if only if all of its diagonal entries are non-zero. Here we're talking, instead of a diagonal matrix, we're talking about a triangular matrix. And so here we're saying a triangular matrix is invertible if only if its diagonal entries are all non-zero. So it extends to not just diagonal matrices, but also to triangular matrices. D, the inverse of an invertible lower triangular matrix is lower triangular. The inverse of an upper triangular matrix is upper triangular. Okay, so when you take the inverse of an invertible lower triangular matrix, lower triangular, the inverse of an invertible upper triangular matrix is upper triangular, right? If it's not invertible, you can't take the inverse. So we're assuming it's invertible to make those statements that they're invertible. Okay. Okay, so then that's that theorem. Okay, so I think those statements are understandable. If you look at if you just try them out with matrices and you multiplied them, and you would see that it would just obviously work out. Okay, so let's keep going. Definition. Okay, a square matrix is said to be symmetric if A is equal to its transpose, A transpose. Okay, so a square matrix is said to be symmetric if A equals A transpose. Okay, example. So the following matrices are symmetric, since each is equal to its own transpose. Okay, so let's look at some of these matrices. So each of these matrices are symmetric. This one is 7 on the main diagonal, 5 on the main diagonal. This is a -3, and that's a -3. Okay, so if you take the transpose of that matrix, if you just switch the rows and columns, it's equal to itself. Okay, so the transpose is equal to itself. And you see that there's a symmetry here off the main diagonal, that this entry is the same as this one. That's what symmetric matrices look like. They have symmetry about the main diagonal. Okay, the entries on the main diagonal can be anything, because if you switch the rows and columns of a matrix, the entries on the main diagonal don't move where they are. They stay exactly where they are. And so there's no condition on the diagonal entries, the main diagonal entries, when you want to talk about a matrix being symmetric or a matrix being equal to its own transpose. Okay, it's off the main diagonal where there has to be a certain relationship between the entries off the main diagonal. There has to be the symmetry that you see here. So let's look at a 3x3 matrix, and then the symmetry becomes more clear, even more clear with the 3x3 one. So those are the main diagonal entries. They can be anything. That if that's 4, that has to be 4. If this is 5, that has to be 5. And if this is 0, then that has to be 0. See how this now, the symmetry is now extended a little bit more. Instead of just this and this being the same, now the 4 and 4, this has to be the same as this. The 2, this has to be the same as this, and this has to be the same as that. So you have this symmetry about the main diagonal here. So that's another example of a symmetric matrix. And then if you have a diagonal matrix, okay, so if you have a diagonal matrix, so that's D1, this is D2, this is D3, and this is D4, and all the entries are 0. This is also a symmetric matrix, because if you take its transpose, it's the same, right? Okay. Since entries don't move when you take entries on the main diagonal don't move when you take the transpose, and so all those entries stay in the same spot, but everywhere else is 0. So even though those move, the zeros move to other spots that are already zeros, right? So, but when you're switching these entries, you're just switching zeros, and so it's still the same matrix after you take the transpose. Okay, so those are 3 examples of symmetric matrices. So the following, those 3 matrices are symmetric since each is equal to its own transpose. Okay, and a remark. A square matrix, capital A, is symmetric if only if A sub ij is equal to A sub ji. Let me see here. For all values I and j. Okay, we're just using another notation for the entry of a matrix. Instead of saying little a sub ij, we're saying it's matrix A, the entry in the ith row and jth column of matrix A. This is the entry in the jth row and ith column of matrix A. So saying that this equation holds for all values I and j is just saying you have this symmetry about the main diagonal. Like if you look at the 3rd row, 1st column, that entry would be the same as the 1st row, 3rd column. As you vary I and j, you're just saying that corresponding entries that when you flip them about the main diagonal are the same. That's what this statement is saying. Capital A sub ij equals capital A sub ji for all values I and j, saying that when you switch the row and column, the entry, those 2 entries are the same. And that's equivalent, has the same truth value as a matrix being symmetric. So that's a remark. Okay. Okay, so we're going to stop there. Okay, so So we're near the end of 1.7, but we didn't finish 1.7 yet. We did finish 1.6. So for homework, you're still here. Homework is for 1.6. So the homework is for section 1.6. Okay. So for 1.6, gotta find it. All right, here we go. Okay, so then that was today 1.5. So the homework for next class, oops. The homework for next class is 1.6. Okay, so this is the homework for next class, 0.6, 3:11:15. 1.6, 3:11:15. Okay, 1.6, 3:11:15. Let me just make sure. 1.6, 3:11:15. Good. Okay, it's due next class Thursday. Okay. On Thursday, 10:12. Okay, so that's the homework for next class. Okay, thank you. I'm going to save the whiteboard now. Okay, whiteboard is saved. Okay, so have a good night. Oh, right. Yeah, 10:14. Okay. Yeah.
Oh, good night, Professor. Have a good one.
Good night. Good night, 10:14. Good night, everyone. See you on Thursday. Thank you for being here. Good night. Oh, I got it. Thank you.